This week we get to talk about exoplanets. Exoplanets are planets that go around some other star other than our own. In this lecture we'll get to talk about how we find these exoplanets, these planets that are outside of our solar system. The ones that we're finding are in our galaxy, just in our little neighboring region inside of our Milky Way galaxy, because these things are really hard to find. So let's take a look at how we can find some of these exoplanets. So, if we're going to look for these planetary systems around another star, first of all, let's think about the logic of that. Okay? If planetary systems are uncommon, when we go out and look, we should find them in very few places. Well, it turns out that when we start looking, we find these planetary systems everywhere. And that makes sense. We think that these planetary systems are developed just like our solar system developed with this solar nebula theory, that as the star forms, planets should form naturally. So we should find systems like this everywhere. Now they may not be just like ours. They may not have 8 planets. They may not have the same kind of planets, but they're going to have planets going around that home star. For these purposes, we've defined that a planet is a body that orbits a star and/or has a mass of less than 13 Jupiter masses. Okay? That mass limit is put in there to define a planet versus, let's say, a brown dwarf, a little failed star. Okay, so sometimes there actually are planets that are all on their own. We call these rogue planets, planets that are not going around a star. So if there is one of those objects, to distinguish it from, let's say, a star or some other object, we have that mass limit. So if it's a natural process, there should be lots of exoplanets, and that's indeed what we're finding now. So if we're going to go look for these planets, it's a little trickier than it sounds. Okay, it sounds like, it would be great. We'll just go and look at the stars and we'll see if there's planets going around them. But usually you can't take a picture of them directly. What you can do is you can look for the effects that the planet has on its home star, usually using some kind of Doppler shift or motion of the star itself. Okay, very hard to find the planets directly. Right? If you've ever seen Jupiter up in the night sky, let's say, right? It's our biggest planet in the solar system. We're in the solar system that Jupiter is in, right? So it's not that far from us. But when we see it in our night sky, it's just a little tiny dot. Even through a telescope, it's still a fairly small dot, right? Maybe a centimeter across. It's not that big, okay? Imagine what it's like trying to find planets in another solar system. Even if they're big like Jupiter, it's going to be very, very hard to see these things, right? So it's much easier to see the effect that maybe a massive planet has on its home star. So let's look at what that looks like, okay? So one of the ways you can do that is if the planet that's moving around that star is massive enough, it will actually, believe it or not, move the star itself. Okay, now our planet Jupiter does this to our home star, right, the sun. It actually, as Jupiter goes around, it moves the sun a little bit, okay? What's happening is these two objects need to maintain their balance, okay? So we've got the planet right here, we've got the star right here, and they need to be balanced around this point right here, this red plus sign. Okay, so notice that the star is on this side of the red plus sign, and the planet's on that side of the red plus line, and that's always going to be true. So as this planet moves, that means this star too has to move, right? So let's watch it move. Okay, so as that planet goes around, so does the star. So if you're looking up in space and you see there's this star that seems to be moving in a predictable fashion, it's not going to be moving far, but this might tell you that, hey, there's a planet going around there. Okay, maybe you can measure some of the mass of the planet. You can measure how far away it is, right? Some other factors about the planet itself. Now this works great if you can see the planetary system, as we call it, face on, so that you can see that full orbit. But often that's not the case. Okay, a lot of times you'll end up seeing this sideways, okay, like we're seeing down here, where this planet's going to go around, and you're going to see this star here in the center, but you can't see exactly how everything's moving. Instead, you're going to use the Doppler shift. Okay, so as things move towards you in the Doppler shift, they're going to blue shift. They're going to move to smaller wavelengths. As things move away from you, they're going to move towards red wavelengths. They're going to stretch out that light. Okay, so what we can do is we can watch for a blue shift or a red shift, and that's going to tell us if this home star in the center is moving. Okay, so it's the same motion as before, but now seen from the side. So let's watch what that looks like. Okay, now it goes pretty fast. Okay. All right, so as that star comes towards us, we're going to see a blue shift. When it goes away, you're going to see a red shift, right? Towards and away. Okay. Both of these processes are using the same phenomenon, okay? That motion of the planet moving that star in the center. Okay, this is what we call the Doppler wobble method, because we're using the Doppler shift to see the wobble of the star. This is what it looks like in plot form, okay, where we've got the speed of the star versus the time. The time in here would tell you how long it takes the planet to go around, right? So notice this is only a few days. Okay, that's a short amount of time for a planet to go around. So when we're looking for these planets, they're not always just one planet, right? If there's one planet, it's pretty easy, right? Like we have here with 51 Pegasi. Okay, there's one planet going around, so that moves the star in a very predictable fashion. When there's more than one planet, you get a messier pattern here, like we're seeing here, okay? Using this method, they have found lots of planets. Now, not all of these were found with this method, but the vast majority were. Okay, so we're talking about almost 2,000 planets, 1,200 planetary systems, and about 500 that have multiple planets within one system. Okay, so we're getting up there, right? We're getting better and better at finding these. It's hard, though. It takes a lot of time to make this happen. There is another way to find these planets. This is using what we call the transit method. Okay, so like the name implies, something's going to move. It's going to transit. And what happens in this one is that the planet's going to move in between us and the star, right? There's our planet. We'll pretend my arrow is the planet. Okay, when that planet gets in between us and the star, it's blocking out a little bit of that star's light. So what we're going to end up seeing is a tiny, tiny, tiny dip in the amount of light we're getting from that star, right? Part of it got blocked out. Part of that light's no longer getting to us. With this method, we can determine some things about the planet itself as well. We can figure out about how big the planet is. We can figure out how long it takes to get across. And sometimes we can actually figure out things about the planet's atmosphere as it goes across. Now we're talking about a tiny dip in the amount of light. Okay, so this is a measure of how much light that star is putting out. Normally it's putting out a full 1. Okay. As the planet moves in front of it, though, notice that that light dips a little bit. Now, it's not dipping a lot, only 1.7% for this one here. Okay, so that's a tiny, tiny difference, but it's visible, and we can find it. There is a telescope that's working on this, called the Kepler telescope. They're crowdsourcing the data and putting it out there for everyone to look at, so you can find that on the internet. This method, though, kind of like the Doppler wobble method, requires that we're seeing this system edge on like this. Okay, we need to see it edge on so that we can see the planet go in front, right? If we were seeing it face on, we'd see that planet going around this way. There'd be no transit, right? So this only works if the geometry of the system lines up with how we're viewing it. Okay, same thing for that Doppler wobble method. We can also do some direct detection. Like the name implies, you're going to see this planet directly. This is hard to do. Okay. It's kind of like seeing a bird in a tree that's, 4 football fields away. You need really, really good glasses, right? Really, really good binoculars or a telescope or something to be able to see that planet or that bird in that tree. So to see these planets, we're going to try and detect the light from the star that gets reflected off the planet, or actually the heat from the planet itself. But this requires a really, really good telescope. So I've got a couple of pictures of those. This has been more recent, right? You can see this is from June 2004. I believe this one's 2005, right? We've got a dwarf, brown dwarf star right here, and there's a little possible planet right next to it. Okay, very hard to find these. This works best when the star at the center is not very bright. Okay, these brown dwarf stars are not very bright. If the star in the center is too bright, it washes out the star here. It's like trying to catch a baseball that's coming at you right in front of the sun, right? You're looking directly into the sun. Okay, you don't see the baseball when the sun is so bright. Same idea here for our detection of planets, right? If this star is too bright, you don't see this little planet over here. Here's another one. This one's kind of interesting. This is Fomalhaut b. There's the planet. Okay, and a little dot in there somewhere, right? It's amazing that they found it, right? But there you go. So most of the time we're going to know an exoplanet's there just because of how that parent star, that home star, is behaving due to the planet, right? Very rarely is it going to be through that direct imaging.